Peace in, YouTube. So I'm Greg from Greg's Tutoring at GregsTutoringNYC at gmail.com, coming at you here. So hopefully everybody's all right. I believe my mic is on. The connection went through pretty well today. So we're going to do the lightning round, which is snippets of stuff. We're going to start inching a little deeper and deeper, working our way deeper through the 8th grade and throwing in some 9th grade questions eventually. I can't remember what I have today because I have just a bunch of questions in a file. But we're going to just keep pushing forward. There's still about a dozen weeks or so, and we're just going to take bite-sized chunks off as we go through each one. So this snippet of stuff is about math stuff, usually smaller problems, but I'm not sure. I might go into some deeper problems today. And most of what we're going to focus on is word problems because we can have a lot of things. Give me 1 second here, because I didn't turn off my notifications. So it was about a 15-second delay here. Okay, so let's just start jumping into some of these things. That should come back in a second. So I'm going to start writing out a problem. The number 303 contains 2 3 digits. So we have 2 here like that. That's the 2 we're talking about, all right? How many whole numbers between 900 and 1,000 not evenly divisible by 10 contain, that's not coming through, so let me raise the camera for a second. Not currently visible, contain at least 1 3-digit. So this is a little different than a lot of the examples I've given, even the ones I'm pulling out from the tests. All right, so let me go back to here and make sure that this actually came through. Yes, it came through. All right. So what we want to do is look at this and kind of give an analysis. There's really only words here. So I've been kind of following a pattern when we come into a word problem, what I've given you that's been based on actual test questions. So this one's kind of different. It's not kind of one that you would see on a state test or something like that. It has a little twist to it. Some people might say it's tricky. I don't like the word tricky. I just think it means it's the English is there and the math is there and you have to match them up. Okay? So let's take it one sentence at a time. The number 303 contains 2 3-digits. So we have the first 3 and the second 3. That's the two of them. So that's just an example. That has nothing to do with the problem except for identifying what a 3-digit is, so to speak. Okay, well, I wrote this up, but they didn't even have to provide that, okay? So the question is, how many whole numbers, so we're not talking about fractions, we're not talking about decimals, okay? We're also talking about positive numbers, okay? Between 900 and 1,000, so that definitely double confirms it's positive. Contains at least 1 3-digit. So for instance, the number 123, it contains 1 3-digit. Okay? And it's not evenly divisible by 10. What is that talking about? So 50 is evenly divisible by 10. It's 5 with no remainder. 55 is not. 55 divided by 10 gives 5.5. 5 with a remainder of 5, so that's no good. And it contains at least 1 3-digit. So you have to come up with a number like 903. 903 contains 1 3-digit. All right, so they're asking between 900 and 1,000. So since it does not say inclusive, then you don't include them. So it's basically talking about from 901 to 999. How many numbers between those two, including 901 and 999, because it's between 900 and 1,000, how many numbers between those two contain at least 1 3-digit? That's, and the number that you're going to bring up for review cannot be divisible by 10 without a remainder. It has to be evenly divisible. All right? So, what could be going on here? So, again, you can pause the video if you want, if you're somebody on the replay. If you're live, you can chime in. I see there's a few live viewers. Well, one way is to just start listing them out. So, for instance, I mentioned 903 before. That's 1. There's also 913, 923, 933, 943, 953, 963, 973, 983, and 993. Okay? And a number like this, it has 2 3s, it counts for 1. It's asking how many whole numbers within that contain at least 1 digit. So what do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 numbers. So is that how many whole number digits we have that are not even divisible by 10? That contain at least 1 3? Is the answer 10? No, because we're not done yet. Because there's all the 30 numbers. In other words, 930, 931, 932, 933, 934, 935, 936, 937, 938, and 939. So that's another 10. We go from 1 to 9 plus there, that's another 10. So that means we have 10 plus 10 equals 20. Hooray, right? No, not hooray. Because it turns out we got 933 twice. We got this for being a multiple of 10 inside of here. And we got this. So we basically picked up this 3 in the first shot through it. And the middle 3, when we counted by the 10s up here, we basically got the last 3. It just so happened to be a double 3. On this one, it also happened to be a double 3, but in this one, we were counting for 30-somethings. So each one picked up another 3, but it only counts as 1. So we're going to have 20 minus 1 equals 19. And we're done, right? Hooray! No, we're not. Because that's not what the problem asks. It also asks that it's not evenly divisible by 10. So what is that talking about? We already explained what that was. That turns out to be 930. That's the 930 number. So we're going to take 19 minus 1 again and get 18. Triple hooray. Are we there yet? Yeah, we're there. So the answer is 18. So this one is one where you have to analyze the words, try to understand what it means, any technical terms like whole number, okay, divisible by 10. You have to understand what that whole phrase means, okay? And then once you figure out those things, including the example, they're giving you the example for a reason, then ripping it apart mathematically and going through each step one at a time. So this turned out to be a multi-step word problem using actually totally different parts. Doesn't matter that they're all related to the same numbers. There might be a formula to do this too, but I doubt it. And this is simple enough. It was not that long. And once you get used to this kind of problem, it's easy to solve. And you'll get to understand the wording, even if, however it's worded, is a little slightly different than the way I'm wording it here. This can come up on the SHSAT. This can come up on a whole bunch of tests, including the Hunter College High School test. Those are the kind of two ones that I would be more concerned, especially for younger kids, because you guys are, if you're taking the SHSAT, you're probably 12 or 13, or if you're taking the ninth grade one, you're 13 or 14. And I could see this question on the ninth grade one as well, all right? And if you're taking the Hunter College High School test, I could see this on that test as well, and you're 2 years younger than at that point. So you could be 10 or 11 really at that point. So this is a nice, challenging, meaty question to chew off for something like that, all right? All right, so let's try another word problem. Do I have scrap paper? Here we go, more scrap papers. Let's go to this. So again, you know, bite-size that off. And even if you want to just, now that I said pause the video before, this is kind of one where you actually want to kind of do it over yourself again on scrap paper, just to kind of make sure you can do it, because you want a real test, you want to have that rehearsal, okay? And then depending on what bounds they give, they may have given it from 850 to 1,050. It could be a 200 point range. It could have been from 903 to 993, just to make sure that you didn't include 903. You know, there's a whole bunch of scenarios there where the problem can be twisted around. I like to look at these word problems as a Rubik's Cube, so that there's the so-called standard question, and then as you twist and turn to match the colors and stuff, they just add, you can either add stuff or vary it up and just tweak it back and forth and back and forth and back and forth. So that you can have one question and just 20, 30, 40, 50 variations of it sometimes. And sometimes all those variations could have totally different ways to address the problem, because when you tweak it, it's not the same problem anymore. It's a slightly different problem. So it may require a different solution to address it. You have to match solutions and problems. Okay? You don't just say, oh, it looks like that, and then the answer must be this way. No, you have to do the analysis on it. And that's the point of the word problem. So you're trying to understand it cognitively and then map it into the right math. All right? So this is a good question. All right, so let's try another one. A company makes bicycles and, cannot fit there, tricycles. Okay, let me scroll this up because a worker lays out the necessary parts on the floor. Okay? He counts 14 handlebars and 33 wheels. Using all parts how many bicycles and tricycles can he make? All right, so let's just read through it again. A company makes bicycles and tricycles. A worker lays out all the necessary parts on the floor. He counts 14 handlebars and 33 wheels. Using all the parts, how many bicycles and tricycles can he make? So maybe somebody just shipped this to them and said, make as many bicycles and tricycles as you can. Maybe somebody already figured it out and said, make us, somebody paid for a bulk order to have the bikes and tricycles made, and this guy is just the guy there to do it. And he wants to kind of double check, because they told him all the parts are there, and he kind of wants to know if they really are, number one. And number two is, well, exactly how many bicycles and tricycles are going to be made. I mean, because he's just sitting there and he's like, wait, I got 14 handlebars and I got 33 wheels. How do I know I have the right amount? Okay? So let's just take it, again, take it a sentence at a time. Company makes bikes and tricycles. The worker lays out all the parts on the floor. Fine. There's kind of no math there. He counts 14 handlebars and 33 wheels. So that's our givens. That's our two givens, 33 wheels and 14 handlebars. Using all the parts. So that's a requirement as well. We're being told we must use all the parts. How many bikes and tricycles can he make? All right, so it seems to me that bicycles have 2 wheels and tricycles have 3 wheels. And both bicycles and tricycles, they all have handlebars. Okay? And we're assuming he has the bodies to them as well, all right? I should have put that in like unrespective bodies or whatever. So how do we kind of confirm this mathematically? Well, the total number of bikes is going to be 14. And we know the total number of bikes, and I mean bicycles and tricycles. The total number of cycles is going to be 14. We know that because it's 14 handlebars. So if we do B plus T, bicycles plus tricycles, equals 14. Okay? We also know that a bicycle has 2 wheels. So every bike has 2 wheels, plus every tricycle has 3 wheels. So we know all the wheels add up to 33. So we're going to get 2B plus 3T equals 33. So now we have a simultaneous equation. We can either substitute or throw one in, or we can figure out a way to do it simultaneously. The past few examples I did where we did the substitution. So I'm going to do this one where we actually make one of the things equal to the other. So the goal is to either be left with B's or T's when you solve this. So we can multiply this by 2 and subtract the 2 of them, so this cancels out, or we can do this by 3. All right? So I'm going to go with making this 2. So if we have 2B plus 2T equals 28. In other words, I multiplied both sides of this by 2. What you do to the left side of an equation, you do to the right side of an equation. So we get 2B, we get 2 times B plus T with the distributive property, 2B plus 2T, and we get 2 times 14 is 28. Okay? What I'm then going to do is just subtract these 2 equations. I have 2B, I take a B away, I get 0. I have 3T, I take a 2T away, I end up with T. And I have 33 minus 28, and I get 5. So the number of tricycles is 5. Because I had B plus T equals 14, then if 5 plus T equals 14, then T equals 9. Sorry, did I do that? I meant B. B equals 9. So we're going to have T equals 5, the number of bikes equals 9. And we can double check it against both formulas. So we originally started out with B plus T equals 14. So 9 plus 5 is 14. Okay? We also had, this was the equation that I mapped from the word problem into here. So we have 2B, which is 2 times 9, plus 3 times 5 equals 33. So we get 18 plus 15 equals 33, and we get 33 equals 33. So that does match. All right? So this is an example, because in a lot of the other YouTubes I did, I was more focused on the raw math and doing basics and cores and fundamental. I still want to emphasize all that here, but I want to also talk about mapping the words into this. And this is going to give you a leg up. And this is where a lot of kids, just over the course of all the kids I ever tutored and speaking with other people, it's always the word problem. All right? And I've seen this on other things. This is where everybody is just like, huh? And it's about attention to detail, and it's about mapping each sentence one at a time. Take a sentence one at a time. Within a sentence, take a phrase, read up to a phrase, process it, make sense of it, read the rest of the sentence, make sense of the whole sentence together, including every phrase within it, Go to the next sentence, do the same analysis, and then combine the two sentences and make a super sentence or a super thought or a super idea and make all that work. And as you go through each one, just keep doing that combination. And as you're going along as well, as you're combining, ask yourself questions. What did they give me? What equation might I be using? Does this make sense? What's the part that's missing? Stuff like that. And then you just start piecing it together so it starts making sense. And as you're doing this, you should be writing down things. Okay? That's how you would get like, wait, if there's 14 handlebars, then B plus T must be equal to 14. So as you're doing this, try to figure out your givens. And sometimes just the act of putting it down on paper, the equation or whatever's necessary is going to leap out. Okay? And sometimes there's a level where you have to take a leap. Okay? And some of this is why you're doing the prep and the studying now. So you have to know that this becomes a simultaneous equation problem. And you have to know to map things like 14 handlebars and 33 wheels based on what these inputs are. There is a leap there. I'll give everybody that you have to make the leap where there's 14 handlebars. This must be 14 cycles altogether. If we're talking about bicycles and tricycles, that's the only two there. And if there's 33 wheels, we have to distribute the wheels back and forth between the bikes and the tricycles. Well, tricycles have 3 wheels and bikes have 2. So now we figured out that we did get an exact number and that the person can make 5 tricycles and 9 bicycles and use all the parts. Okay? All right? Okay. So again, word problems. That's what we're trying to look at here. Let's see, when did I start? I'm about 20 minutes into this. I'm going to do another problem or two. Again, these are slightly deeper than some of the other lightning things. The other lightning stuff was focused more on square root, exponents, things like that. And by the way, we still need to do things like that. But I also want to jazz things up. There's so many topics to cover. By the way, this kind of relates back to you guys asking me, which topics? What about the ELA? All this other stuff. There's dozens and dozens of topics. And at the end of the day, you have to know them all. Okay? Not only do you have to know them all, but you have to do things like the mapping from the math into the English and back from the English into the math. Both ways. You have to know how to speak math. Right? We're talking about a number sentence. It's a number sentence. We're mapping the English literally into the math. Right? So there's some cognitive process there that's logical, and intellectual, and cognitive. We need to make that leap. And that's what some of this is about. And that's why the SHSAT is different than, say, the state test. Even though the state test or the material for the Common Core grade 7 and grade 8 and things like that, even though they're the basis of this, we have to make that leap into the other side of all this. All right? So, all right, let me see what other problem I might have here. That's great. All right, here's one that builds on some of the stuff we've done in some other problems. So, the QB99 local bus leaves SHSAT Central every 21 minutes. The QB99 Express leaves SHSAT Central every 18 minutes. Okay? If they both leave at midnight, how many times a day do both buses leave together before finally heading to the depot? All right? So the problem resolution to this at this point, especially for anybody who's been following my scopes here, my YouTubes, has to know at least partially which solution mechanism is necessary here. But in any event, let's take it a step at a time. Okay? The QB99, which is a bus that goes between let's say it's a bus that goes between Queens and Brooklyn. That really doesn't matter. It's the 99 because I like the word 99, the number 99. So the QB99 local bus leaves SHSAT Central every 21 minutes. Okay, cool. So it goes about 3 times an hour, a little more than that because it's 2.9 or something. If it was every 20 minutes, it would be 3 times an hour. The QB99 Express leaves SHSAT Central every 18 minutes. So there's a couple more. That one actually gets in the 3 times an hour with a few minutes left over. So one is almost an hour with a few minutes over, and the other is a little under an hour. You could argue it's not really much of an express. Well, if you're waiting for the train or the bus in the rain or in the winter, you're going to take those few minutes. If they both leave at midnight, meaning they're leaving SHSAT Central at midnight, that great train station where you transfer to these buses, if they both leave at midnight, how many times a day do both buses leave together before finally heading to a depot? In other words, at midnight, they both start out. They come from the depot, they go to SHSAT Central, that's their first stop, and they're both going to leave there. And then through the day, the local comes every 21 minutes, the express comes every 18 minutes. When do they see each other again? And furthermore, how many times do they see each other through the whole day? All right? So this is a what kind of a problem? And since this is a word problem, we know there's sometimes multi-steps here. So that's a hint too. There is a multi-step here. There's at least 2 steps here. So because we have every 21 minutes and every 18 minutes, and they both leave on time, and how many times do they see together, those are all keywords, and there's nothing else funny going on here. So this is an LCM problem. So again, you can do LCM a couple of ways. Let's just take the 2 numbers, 21 and 18, and get their prime number factor tree. I could do it graphically. Since these are simple, that's 3 and 7, right? There's no other divisors here, and this gives us 2, 3, and 3 when we map it out. That's a 7, not a 9. 2, 3, and 3. All right, and we're left with prime numbers here, so we're done. That's the prime factors of each of these. So when we do the LCM, we're finding each unique factor and finding the largest grouping of it. So I like to just start with the lowest number first. 2. There's only 1 2, so we're done with 2. 3. There's this versus this. Well, we're getting the largest grouping of it, so there's 2 3s. And the only thing left is 7. There's only one of those. 7. All right? So we have 2 times 3 is 6, times 3 is 18, and then 18 times 7, we get 80 plus 56, so we get 126. I can do that backwards. 7 times 3 is 21, times 3 is 63, times 2 is 126. So that's what I get, 126. The LCM of 18, and this is 126. So since 18 and 21 were minutes, then this is minutes as well. So now that we have some result, let's kind of feed it back into the question and see what's kind of going on here. So the Q99 leaves every 21 minutes. The Q99 Express leaves every 18 minutes. They both left at midnight. How many times of the day they leave together before they... Okay, so this means in 126 minutes they're going to meet up again for the second time. The first time was at midnight. In 126 minutes, about a little over 2 hours later, they meet up again. But that's not the question. The question didn't say when do they meet up again. The question said how many times a day do they meet up. So what do we need to do next? So this is where it becomes a whole nother problem. So I like to think of this as throwing away the original problem and rewriting it to this new problem. Because if we solve the existing thing successfully, we don't care about that anymore. I mean, we should double check it and confirm that it's correct, yes. But otherwise we're done with that. And now we have a new problem to solve. It's the second part. And that's what problem solving is about. You're trying to divide and conquer and rip things apart into sub-pieces. And it could be, and when you're creating larger problems, building a building, making an aircraft, doing something new, like inventing the iPhone, there's a whole bunch of subsystems that are often independent. And there's also ones that are dependent. They're interrelated and they're connected as well. So you have to adapt and be able to ready for all of those. And one way to tackle a large problem is to break it down into smaller problems. All right? Okay, so we have 126 minutes. What the heck do we do with it? Well, it says how many times a day does it happen? So we can map that into hours. I don't think that's going to help us, although we could leave it that way. What I'd rather look at is it's asking how many times a day. So we need to do it 24 hours, okay? But this is in minutes. So instead of converting this to hours and getting a fraction, let's try to deal with whole numbers as long as we can. So 24 hours times 60 minutes is the number of minutes in a day. And that's 1440. And by the way, I mentioned about things like 3 times 17 coming up often in tests, or 16 times 16 and 13 times 13. This number comes up often enough as well as 5280, the number of feet in a mile. And if anybody doesn't know, I'm just going to throw this out. 3 feet equals 1 yard. A lot of kids forget this, especially in early grades, especially during the state tests. But please don't forget this during the SHSAT. It's not something, everybody doesn't measure yards every day. So it's an easy number to not really have, immediately fluid in your head. Okay? Okay, in any event, there's 1,440 minutes in a whole day. So if we divide the two of those, 1440 divided by 126, we should get the number of times they meet up every time. And there might be a fraction there. We don't know yet, right? We don't know yet. So why don't I do the division? And again, remember there's no calculator on the SHSAT. So be careful with this. This is an ugly one. So 126 goes into 1, no times. Goes into 14, no times. Goes into 144, 1 time. And we end up with what? 18 back? Yeah, we have 118. So then we drop down to 0. So 126 goes into 180 one more time. So I ran out of space at the bottom here. So I'm going to do 180 minus 126. I think it's 7145. We're going to get 54. So we're going to get 540 is what we're trying to shoot for now. Okay? So 125, 125, I'm going to estimate this. Or even 120. 120 times 4 is 480. 120 times 5 is 600, so that's too high. So I'm going to go with 4. 540 times 4, we're going to see that. 0, 4 times 4 is 6, 1. 21. So I get 2160. No, I did that wrong. We're trying to do 126 times 4. Sorry, people. 6 times 4 is 24, 2, 8, 9, 10, 0. So we get 504. So that's 4. 540 minus 504 gives us 36. So we're trying to shoot for 360 in here. Anyway, we're at this point, we don't care the digit because we know it's 11 times, 11.4 something times they met. You can double check the 126 times the 11 just to make sure you're getting some number that's reasonable. You're going to get 126 plus 126, 0, 6, 8, 3. You're going to get 1380. If we added one more 126 to that, 601, 345, yeah, we're over. So 11.4 works. So this means the buses met each other 11 times that day. All right. So again, this is a nice word problem, and I think I'm going to stop in this one. So we didn't do too many of these, but they were a lot more meaty meatier than the past ones. Yeah, hi Leo. I'm ending now. Hit the replay. I went deeper on this one. Sorry, I just got distracted for a minute, and so I'm going to kind of start gyrating into that, even though there's a lot of other topics, so that we're getting overlapping stuff. And by the way, you guys are mentioning about ninth grade stuff. Some of these could be ninth grade questions. All right, guys. Everybody chill out. Have a calm, peaceful day, and I'll return tomorrow or whenever I can be free again. I'll probably do an AMA, pop out an AMA later in an hour or so. So, in any event, toodaloo, everybody. Please like and subscribe so that we can help each other. All right? Thank you, guys. Bye.